Hi, we are meeting once again in the lecture series of Statistics and Management Studies. In the last class, we discussed duality in linear programming problem. Today, I am introducing simplex method to dual problems, solving a linear programming problem by using simplex method, and before that transforming the problem into duality. Primal problem, change it to dual, then apply simplex method for convenience. In this class, discussing that procedure instead of big M method for convenience. Now the problem is to solve a LPP by simplex method. As we know, to solve a problem by simplex method, it should be presented in standard form. That is, the objective function is of maximization. And linear constraints are having less than or equal to sign linear constraints and non-negativity conditions as usual. But this problem is different one from the standard form. In this problem, the constraints are having greater than or equal to sign, greater than, and the objective function is of minimization, minimize. So it is not in a standard form. In such cases, we use a method known as big M method. That is by using artificial variables. It is comparatively a lengthy process, numerically as well as subject-wise. So I am discussing this problem, avoiding the big M method by applying the duality of linear programming problem, dual LPP, That is, we discussed earlier, every problem has a complementary problem. It is called dual problem. So, for convenience, this problem is transformed into another one termed as dual problem and try to solve by its duality property. Then how will we formulate the dual problem? We know that the constraints, objective function and variables, everything is changed. First one, the problem is of maximization. Here it is minimization. So we change into maximization. Constraints, maximization. Constraints are changed to less than or equal to sign. This procedure is known as duality. So I am first presenting the dual problem of this one. That is, we have to decide about the number of variables. The number of variables is equal to number of variables in dual problem is equal to the number of constraints in primal problem, So we are using this. The dual problem is presenting directly. Dual problem of this is changing into maximization. It is a problem of maximization. Maximize Z dash is equal to changing the cost coefficients and availability coefficients, interchanging this. And how many variables? The number of constraints. There are 3 constraints. So we use 3 variables. So maximize 25y1. Introducing a variable y1 plus 24 by 2, another variable by 2, plus 60 by 3, 60 by 3. So we introduce three variables, y1, y2, y3, and the constraints are the transpose of the matrix, that is y1 plus 4y2 plus 3y3, y1, 4y2, 3y3, constraints changed into less than or equal to the coefficients, the availability coefficients and requirement coefficients and the cost coefficients. The requirement coefficients cannot be changed. Availability coefficients are finite. They are changed. That is less than or equal to 9 and 2y1 plus 3y2 plus 2y3 less than or equal to 10. y1, y2, y3 greater than or equal to 0. That is the dual LPP. From the given problem, we formulate dual LPP. Then dual of this dual is the same. This problem, dual of the dual is primal. As we discussed earlier, dual of the dual is primal. So the problem is transformed into maximize z dash is equal to 25y1 plus 24y2 plus 60y3 subject to constraints. Here the number of variables y1, y2, y3, there is a number of constraints in the primal problem. Number of constraints is equal to the number of variables, two constraints. So this is a dual linear programming problem. So this is the dual problem. We are discussing for the dual problem. That is, the duality is going to discuss here. But in the last session, we discussed simplex method of standard LPP. This is standard LPP. Maximize Z dash. We use Z dash since it is a dual problem for knowing or for remembering that. Subject to every step of this problem is discussed in the earlier class. Once again, we are going to discuss this. What about the first step? The inequalities are changed into equalities by adding slack variables, that is y1 plus 4y2 plus 3y3 plus s1 equal to 9. 2y1 plus 3y2 plus 2y3 plus s1 equal to s2 is equal to 10. s1 and s2 are two non-negative variables such that y1, y2, y3, s1, s2, every variables are non-negative, greater than or equal to 0. So this problem is ready for applying simplex method to a standard problem. It's a problem of maximization subject to less than or equal to constraints. It's a problem of standard LPP. We are going to apply first iteration table. Simplex method is an iterative procedure. So we are going to present the data in a iteration table. The first iteration presenting here. The components of the first iteration table is so familiar to us. Starting from basic solution, there are two variables, S1 and S2, two basic variables. Its cost 0, the cost 0, and the basic solution is S1 equal to 9, S2 is equal to 10. That is the basic solution. And what about the coefficients? y1, 4 by 2, 3 by 3, 1 s1, 0 s2. Second constraint, 2y1, 3 by 2, 2 by 3, 0 s1, 1 s2. The factors are presented. Then we are checking for the quality of the solution, whether it is optimum. For that we calculate Z. Z is equal to 0 into 9, 0 into 0, 0 into 1, 0, 0 into 4 plus 0 into 3. Every element in the first table are zeros. Whether we are happy if you get 0 total profit. No. So we are calculating Z minus C. Revenue minus cost. 0 minus 25. Minus 25. Minus 24. Minus 60. 0. 0. This is not optimum. If all Z minus C values are positive, then the solution is optimum. Therefore, this first iteration is not ready for optimum. So we have to improve it. How? Two factors are to be decided. Which one is coming into the solution? Which one is leaving from the solution? Which one is coming? Among these values, choose the variable having the maximum negative minus 60. That means 60 related to Y3. Y3 is coming into the solution. Y3 is coming. So which variable is going? We can ratio 9 by 3. 9 by 3 is equal to 3. 10 by 2. 10 by 2 is equal to 5. This 9. 9 by 3. 10. 10 by 2. The basic solution divided by the number in the pivot column as we discussed in the earlier class. So this is just the minimum ratio. 3, 5. 3 is minimum. It implies or it denotes that yes, 1 is going out. Y3 is coming in. So we modify the second table. For convenience, I am drawing in a single table. That's an extension of this. Headings are there. What about the elements? 0, S1. S1 is leaving out. Y3 is coming. Y3. Cost of Y3? 60. 60. Then we have three terminology. Pivot row, pivot column, key number. Which one is the key number? The number which is common. That is 3. 3 is the key number here, which is common in the pivot row and pivot column. Using that, we formulate the new table. Each element in the pivot row is divided by key number 9 by 3, 1 by 3, 4 by 3, 3 by 3, 1 by 3, 0 by 3. The other elements are calculated by the formula. You remember that? Old number minus number in the pivot row into pivot column by key number. Please refer that. I am giving the numbers. S2 is here. Its cost is 0. And the new elements are 4, 4 by 3, 1 by 3, 0, minus 2 by 3, 1. And the corresponding Z values are 180, 20, 60 to 1 by 3, 16 to 4 by 3, 80, 16 to 1, 60, 20, and 0. Then Z minus C values are minus 5, 80 minus 24, 56, 0, 20, 0. We are not happy now. Why? One of the number is negative. So we select that. That is, we select it is the coming vector, coming variable. Y1 is coming, and who is the leaving vector? We find the ratio. 3 by 1 by 3. 3 by 1 by 3 is 3 divided by 1 by 3. 3 into 3 by 1. 3 divided by 1 by 3. That is equal to 9. Other one is 4 by 4 by 3. 4 divided by 4 by 3. 4 into 4 divided by 4 by 3. That is 3. 4 into 3 by 4. 3. Set the minimum ratio. Minimum. So S2 is going out. And X1 is y1 is coming in. We are going for the next iteration. 1 to the third iteration is required. Going for the third iteration. Since we discussed iteration in detail in the earlier class, I am escaping that steps. The third iteration is presenting here. S2 is left out, y1 is coming in, and the computations are. So we are familiar. Here Z values are and Z minus C values are. Z minus C values are. All are positive. All Z minus C's are positive. Therefore, this is the optimum table. The solution is optimum. Optimum. Then we have to discuss some points here. Here we are starting with the problem. Maximize Z dash is equal to 25 y1 plus 24 y2 plus 60 y3. That's the dual problem. What about the solution? This is our solution space. This is solution space. We get y1 is equal to 3. y3 is equal to 2. Here y2 is not here, not here. That means y2 is equal to 0, 0. Then what about the maximum value? Maximum Z dash. Maximum Z dash is equal to, the computation is not required. Here, it is here. There is 195. You may check it. 25 into y1, 25 into 3, 75 plus 25 y1, 25 into 3 plus 24 into 0 plus 60 into 2, 75 plus 120, 195. But this computation is not required. It is here itself. But it's a long but. Why? We reach in a situation that the question is of minimization and we reach at a problem of maximization. That is the difference between the given problem and the answer we arrived. So we have to answer the given problem. What is our problem? Minimize. Z is equal to 9x1 plus 10x2. Minimize 9x1 plus 10x2. Here we derived y1 equal to, y2 is equal to. Therefore, the question is one, the answer is different. From where you get the answer? Minimize. That's here itself. Minimize. Minimize. Z is equal to 195. Maximum Z dash is equal to 195. Then what is the value of x1? What is the value of x2? That is the difference. That's here. It is simple compared to big M method. We get directly from the dual table. X1 is 35 by 2, 35 by 2. And x2 is 15 by 4, 15 by 4. And the maximum Z is 195. You may check it. That is 9 into 35 by 2 plus 10 into 15 by 4. This will get 195. 195. You may check it. So this is more simple, more convenient than the big M method. If the problem is of minimization, all constraints are greater than or equal to, we use dual simplex method. And remember this point, here we get the solution, here we get the solution of the dual. The solution of the primal is here. So this the problem is solved. The answer is minimum Z is 195 and x1 is 35 by 2 and x2 is 15 by 4. One more class is coming to an end point. I think that this is sufficient for solving a minimization problem having sign greater than or equal to instead of using big M method. the next class we meet again with a new subject. Thank you.